So welcome to this first presentation. Paul mentioned that in the DAC adaptive layer, we actually create the sensor-mediated contingencies that are later stored in the contextual layer. So in this presentation, I want to present you the details of how the sensor-mediated contingencies are learned during the interaction with the environment. So the adaptive layer is a model for classical conditioning. This is an example of classical conditioning, air path conditioning on a rabbit. We have the unconditioned stimulus, that is the air path, that is directed towards the eye of the rabbit. That then will trigger the unconditioned response, the closing of the eye. And then this will be paired with a conditioned stimulus, that in this case is the tone. And over the presentations, the rabbit would actually learn to close the eye before the air path. So this is behavioral learning. On the other side, when we then look at the response of the neurons in the auditory cortex, this is the case we've done here, there is the preconditioning response. Well, see, this is a neuron that reacts most to 9.5 kilohertz, but then after conditioning, and the conditioning frequency was at 9 kilohertz, the tuning of this curve shifts. So this shows that actually classical conditioning captures both the perceptual learning bit expressed in this changing of the tuning curve, but then also the behavioral learning, that is the learning of the conditioned response. So in DAC, we try to incorporate the classical conditioning paradigm in the adaptive layer. We have the conditioned stimulus, the unconditioned stimulus, and then the conditioned response and unconditioned response. So how does it translate to a robot? If we have a robot in an arena, there's a specific task we designed to test perception and behavioral learning. We see the robot here. The robot is equipped with a camera and with proximity sensors and light sensors. The target will be the light that we designed then to be the unconditioned stimulus. We have patches on the floor that are seen by the camera that points towards the robot on the floor. And these are the conditioned stimuli. If we look how this would look at in the simulation, we can see first the robot has not yet learned to turn toward the light. But then over the different trials, the robot learns to associate the conditioned stimulus, in this case the patches, to the unconditioned stimulus, this is the light. But then also to other patches, through the perceptual learning, the robot learns actions that are arbitrary. So if we look at the fast dynamics of the system, I forgot some stuff.
Okay, stop. From the beginning.
Can I say something here?
Yeah.
I'm sorry. I just continue?
Yeah.
If we look at how from theoretical...
Do you want me to answer your question?
No. From a,
What do you want to show us?
nothing, I just want to continue here. Okay. From a theoretical side, perceptual and behavioral learning are treated often separate. For perceptual learning, there are mostly statistical learning methods, but for behavioral learning, there is reinforcement learning or then more symbol-like structures to learn the behavior of the animal. But as we see here in this experiment, perception and behavioral learning are tightly interlinked. So in DAC, we try to capture this interlink between perception and behavioral learning in the adaptive layer. So what we see here is the overview of the DAC architecture with the adaptive layer here based on the reactive layer. We have the conditioned and unconditioned stimulus, but then also the conditioned response and the unconditioned response. Now, to be able to unify perception and behavioral learning, What is necessary is this basic principle underlying both, and we propose in the distributed adaptive control architecture predictability as this unifying principle for perceptual and behavioral learning. To test perception and behavioral learning, we have designed a very specific task. We have a robot in the arena. Here on the bottom we have the robot. The US, in our case, will be the light that is represented by the star. The light has radiation around this red area where we trigger unconditioned response, but then the radiation is visible, light is visible over these 3 patches here, but not at these patches. So the task would then be to associate these patches that are the conditioned stimuli to the actions corresponding to the unconditioned stimulus leading towards the light. The robot is placed at different positions randomly and has to learn the different 3 actions at the red, the yellow, and the green patch. So this is the field of view of the robot. So it just sees the patches in front of him. And this is then a video showing the behavior of the robot. We see that it learns the association of the patches towards the light. But we will also see that it will also learn associations to the patches that are actually not directly linked to the light. And this is then exactly the parts where we can distinguish in perceptual learning and behavioral learning. So the behavioral learning is the learning towards the light, doing the precise action. But as in DAC, we only have one weight learning for the perceptual and behavioral learning. We also see that the perceptual learning will drive the actions also for patches that are not related to the US. Now, to then distinguish this these 2 forms, we have also experiments when we can shift the different patches, and we can see how the robot adapts to these dynamic environments where we change the patches. This slide shows the architecture of the adaptive layer. We have on this side 3 neuronal groups, where here one group represents the unconditioned stimulus, what would be the light in this case. On this group, that is a CS group, we have 2 parts. One is the input, that will be this X, where we just have a transformation of different colors to parts of this neuronal group. And this will then lead to the internal states where Y will be the conditioned response and R will be the unconditioned response directly triggered by the unconditioned stimulus. Through that, we then also have a backpropagation that will be the prototype. The prototype is this information stored in the contextual layer and is an approximation and a generalization of the direct input of the camera. If we look at the fast dynamics, we see that if this is the weights that determine the reactive layer, and these are the weights determining the adaptive layer, we see that as just forward projections. And so this means that R is just V transpose S, where Y is W transpose X. Then the prototype is a back projection of the Y towards the CS group, so that E is WY or WW transpose X. And mathematically, this corresponds to a linear projection of the Y towards the CS group. If we look how this will then react, we see first, just at the CS, we see that whenever the patch is in front, there's a group lighting up here. We see that when the robot is in the light, we see there's activity here, that it's transformed here in an unconditioned response. And this is before learning. So we have only little or no activation of the conditioned response due to random connectivity initialized before learning. So, but then we will look at the slow dynamics. So how does this W change over time? we have to see how we incorporate behavioral and perceptual learning. Now, in the terminology I have given you of the prototype and the input, perceptual learning just means we want to minimize the error between the two. So perceptual learning corresponds in minimizing this value, that is the square error of the input and the prototype, so the CS and the prototype CS. On the other side, behavioral learning can be defined as the difference between the unconditioned response, R, and the conditioned response. So we want to minimize the difference between these two responses also in the square. So if you look from a term of prediction on these two terms, it's just that perceptual learning means we want to predict the external world, given our internal state, and the behavioral learning would then mean predicting the consequences of our actions in the world, given our internal state. If we just want to minimize these two functions and we apply gradient following, this is then the formula we'll get to, just by applying the math. So first of all, what we see in this formula, just go through it step by step, is the difference between X and E, the prototype and the CS. That would be here green. But then this differences is modulated by the activity we have in the internal state, Y plus R. So whenever I have a difference between what I see, the X, and the prediction of my X, I learn. But then this learning is modified by the activity in my internal state. So it's not clear in advance what I should learn if I have no conditioned response, or what I should learn from the unconditioned response. And for that, we just parameterize, and this will then be a parameter of the model that we can test how they influence the behavior and the perceptual learning of the robot. On the other side, this is the second term that is linked to the behavioral prediction, is the difference between R and Y. So whenever my prediction of what behavior I should do is not the unconditioned response, or when I cannot predict my unconditioned response, I will learn. But I only learn when my prototype is not 0. So only when I already know something about the stimulus, I will learn. So the intuition that we can take from this formula, from this last part of the formula, is that as long as I've not yet learned what is the correct behavior to dispatch, as long as I don't know about dispatch well, then I sure I cannot yet know what is the correct behavior for dispatch if I don't know what dispatch is. And again, here we have a parameter rho that will be then the second parameter we vary to see over different parameter range what is the influence of this behavior prediction term on learning